Hi there, everybody, and welcome to Physics 2 on this lovely Friday afternoon. Today, we're going to be wrapping up modern physics and ending all of the new content. That means on Monday, we're starting review. All right, here we go. Today, technically, our topic is properties of waves and particles, but really it's a look back through all of the important stuff that we've looked at having to do with modern physics. As always, we're going to start with a lesson overview, where we'll look at what we're going to be doing today. Then we'll go through our daily warm-up and work on the problems that we left you with at the end of the previous lesson, and then ask some questions to help us warm up for this lesson. Then we'll go through what you need to know, really everything there is to know about modern physics all in one shot. We'll work through some guided practice, some questions from the College Board to make sure that you absolutely understand what there is to know about modern nuclear physics. Then we'll do a quick debrief and summary, talk about what we talked about and make sure that everybody's walking away with the same understanding. And at the end, we'll give you some AP exam practice, which we'll start with on Monday's lesson. So as always, I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Rady High School in Frisco, Texas. So let's go ahead and go through our lesson overview today, where we discuss all the different topics we're going to talk about today. So the first topic is quantum, atomic, and nuclear physics, where we'll go back over the things that we talked about in systems and fundamental forces, radioactive decay, energy in modern physics, mass energy equivalence, properties of waves and particles, and the photoelectric effect.
Here's what we think you already know. I'm hoping you know about the wavelength, velocity, and frequency of light, because I feel like we mentioned that a couple times. I'm hoping that you know how to calculate the kinetic energy for a moving mass. Electrons, while very light, they are still massive. When they move, they have kinetic energy. I hope you are well-versed in momentum and collisions. Your AP Physics 1 class likely talked to you about conservation of momentum. We'll be dealing with that a little bit more today.
And by the end of the lesson today, we hope that you can describe experiments that show light's wave nature or particle nature, and describe situations in which matter exhibits wave properties, use conservation of energy to describe a photoelectron emission, calculate the binding energy from mass defect, and distinguish between the types of radioactive particles.
Yes, so a really light day, we're taking it easy on Friday. Not. Here we go. Here comes the warm-up. I hope you're ready. We left you at this yesterday. Ultraviolet light with a 200 nanometer wavelength. It shines on ytterbium. It's a thin foil. The work function is only, 3 electron volts. What probably happens? Well, right off the bat, I want to tell you it's okay to do something that my high school teacher, Mrs. Shear, told me. She said, Joe, if you don't like the way I write the numbers in a problem, you cross them out and you fix the units. I don't know about you, but I wasn't real good at centimeters and meters. So I would cross them out and I would write in the standard units. If it was millimeters or whatever, I would always convert right in the problem. So you can do that. You can cross out 200 nanometers because you don't like 200 nanometers. What's a nanometer? It doesn't even matter in this problem because this is a problem about energy. But wait a minute, a 200 nanometer photon, how do we calculate the energy of that photon? Well, in yesterday's class, we said the energy of a photon is 1240 electron volt nanometers divided by its wavelength. So that is a 6.2 electron volt photon. Oh, that's great. 6.2 electron volts shines on ytterbium, only needs 3 electron volts to get rid of that electron. You know what? It ejects an electron. It has enough energy that one photon ejects 1 electron. So, hey, option 2 is out. Option 3 has a lot of stuff in it, but is ultimately not useful. Option 3 does not describe the photoelectric effect. It's not related to the size of the particles, but I want to draw your attention to the 4th option. It's in here because I think it's a really attractive wrong answer. It says the UV light ejects 2 electrons, because the energy of the incoming light is equal to 2 times the work function. And while that's true, it's not possible. I write a lot of the questions for the AP Physics 2 exam, and the AP Physics 2 Development Committee, in selecting those questions, they love picking questions where sometimes the because is correct, but the claim is not. If the claim is right and the reasoning is wrong, then the answer is wrong. The UV light doesn't eject 2 electrons. It can't, even though it has the energy. Let's take a look at this exam practice problem. We have light shining on a metal foil. Electrons get ejected. Classic photoelectric effect problem. But what is the meaning of that flat part of the graph from a frequency of 0, essentially no energy in the incoming photons, to that F0, that critical frequency where photo emission starts? That little flat line, that represents light that doesn't have enough energy to cause photo emission. Light with too big a wavelength or too low a frequency. There's not enough energy to liberate those electrons. If a different metal were used with different properties than the first one, what might change? Well, I know there are only a few properties of a linear graph that we can change. There's the slope, but you may remember from yesterday, the slope of this graph is Planck's constant. That's h. Regardless of the material used, the slope is still h. But using a different metal means a different y-intercept, because the y-intercept describes the work function of that metal. Different metal, different y-intercept, different vertical shift. All right. Whew. Mr. Eaton, take it away while I catch my breath.
That was a lot to talk about. All right, so we have 4 different reactions here. And basically, we just want to know which X inside of those formulas could be a positron. And by the way, a positron has the same mass as an electron, but it's a positive charge. I'll give you a second to look through which one you think might be a positron. Okay, now that you've had a moment, hopefully, to look through them, I know if it's a positron and it's maybe ejecting a positive charge, I'm either subtracting that positive charge or adding that positive charge. So for instance, look at the last answer here. It's a 12,6 carbon, and it's adding a positive charge to give me 13,7 nitrogen plus a gamma ray. That looks like it could be relatively correct, except the problem is that the mass number is changing. The mass number of carbon was 12, and the mass number of that nitrogen there is 13. So I think in order for this to happen, I'm only taking away from the atomic number and not the mass number. So if you look at the second answer, I'm only taking away the atomic number. I'm changing my atomic number of oxygen of 8 to 7 for that nitrogen, and my mass number is not changing. So that one is the correct answer for which X is a positron.
Okay, next warm-up question. It's just a warm-up image. There's a couple things I want to draw your attention to. You may recall that when we were talking about optics, we talked about the fact that light could be polarized. And we also discussed the idea that light was this electromagnetic wave, this shifting passage of electric fields and magnetic fields, inducing each other through space according to Maxwell's equations. All of that is true, but how much of that do you really need to know on a high school exam or university entrance exam? Well, according to the College Board, the question they asked about this had to do with a few different things. First off, the question was, is there evidence that this wave is polarized? Well, you can tell that the electric field is oscillating in only one dimension. The magnetic field is oscillating in only one dimension. So yeah, this wave is polarized. What is the direction of transmission of this wave? Is it transmitted along the y-axis, along the z-axis, or along the x-axis? Well, for a transverse wave, the direction of transmission is perpendicular to the direction of the disturbance of the medium. So the only direction that's perpendicular to the electric field and to the back and forth magnetic field is the x direction. Okay, I hope your brains are warmed up. I know mine is. Here's what you need to know.
All right, from today's lesson, what you need to know are the different fundamental particles. So we'll review what those fundamental particles are. And you'll also need to know that Electrons orbit the nucleus at discrete energy levels. These are all things that we've talked about. We're just kind of going back over it real quick. You'll need to know about radioactivity and the strong force and what it does. You'll need to understand half-life. You'll need to know the different types of radioactive decay, alpha, beta, and gamma. Those should ring some bells. Relative motion at relativistic speed, photoelectric effect, and how does that show that light acts as a particle, and diffraction of electrons, and how does that show that light acts like a wave?
So today's lesson is essentially a review of what we've learned from modern physics. I heard from some of my own students that this information has been coming really, really fast, and they're feeling very overwhelmed. So I'm hoping that we can settle some of that down for you. The official slogan of AP Physics, I don't know if you know this, is everything is going to be just fine. Okay, take it away, Mr. Eaton.
All right, so let's go back over fundamental particles really quick. Here's a couple of examples at the top. We've got electrons, neutrinos, photons, quarks. Those are all examples of fundamental particles. Now, neutrons and protons are composed of quarks. Hopefully you kind of remember us talking about quarks before. It's a funny word, but that's what they're composed of. And quarks have a fractional charge. Up, charm, and top have a charge of positive 2/3, whereas down, strange, and bottom have a charge of negative 1/3.
And there are some important things that we taught you about atoms. First of all, the idea of atomic number versus mass number. That was in one of the warm-ups. The atomic number of an atom is equal to the number of protons in the nucleus of that atom. It identifies what that element really is. The mass number of an element is the number of protons plus the number of neutrons. It's equal to the total number of nucleons in the nucleus of that element. And the number of nucleons determines what isotope that element is. An isotope is just a different version of an atom.
All right, and we also discussed energy levels. We had a couple of practice problems, a couple of exam practice problems over it as well. And what we looked at was the observation of the spectra made it obvious that atoms emit and absorb energy only in discrete amounts. Discrete just means very specific numbers. And an electron can only have a certain set of orbits, no others, aka energy level of 1 or 2 or 3. There's no in between. And an atom, therefore, has to have discrete energy levels analogous to standing waves. We discussed how that kind of correlates to what you talked about with sound and pipes and strings and that sort of thing.
A P1 callback, love it. But in P1, we talked about how waves transfer energy without transferring matter. And when we started this lesson, we talked about how light can be treated like a wave. But recently, we've been talking about evidence for light as a particle. And some of the primary evidence that we can treat light as a particle is that light can be emitted in discrete amounts. So we talked about electrons absorbing specific amounts of energy or emitting very specific amounts of energy. The emission spectrum of a material shows the light that can be emitted by that material. The absorption spectrum shows the light that can be absorbed by that material when electrons make very specific jumps between those energy levels.
All right, and when that electron jumps from different energy levels, it gains or loses energy that's equal to the difference between those energy levels. And electrons can gain or lose energy in the form of a photon. When they gain energy, they're absorbing a photon. When they lose energy, they emit a photon. The equation that you see in the middle of the screen helps define the energy difference between those levels. So when a photon is absorbed, it promotes the electron to a higher energy state. It moves further away from the nucleus, at least in our model. Only certain wavelengths can be absorbed by the electron. And the list of photon wavelengths that cannot be absorbed is called the absorption spectrum. Again, that was that one that had black lines on the color, the Roy G. Biv bar. And absorption spectrum has missing lines. I think we have an example of that coming up.
Oh, I think we do. Here is a question about the energy levels in an atom and the photons that they emit. So this energy level diagram for a hypothetical atom. Which of the labeled transitions produces a photon with the shortest wavelength? Yesterday, we asked you about the photon with the longest wavelength. So this is probably the opposite answer. Short wavelength. I hope you're thinking high energy. Short wavelength is a high energy wave. Little wavelength, big energy. And the biggest energy jump is transition D. But the follow-up question is, what is the wavelength of each emitted photon? Now, I've gone through and written in the energy difference for each emitted photon. Transition A emits a 3 electron volt photon, whereas transition D emits an 8 electron volt photon. But do you remember how to calculate the energy emitted when a photon changes levels? I'm going to assume that you said yes, but how do you do it? Exactly. It's 1240 over the energy. Good job. 1240 divided by 3 electron volt, that's 413 nanometers. For a 6 electron volt photon, it's 207 nanometers. If the energy difference is 2 electron volts, 610 nanometers. And for that last energy difference, the one that we said had the smallest wavelength, it's only 155 nanometers. Notice that a bigger energy difference means a smaller wavelength. So C has the smallest energy, but the biggest wavelength. D has the most energy and the smallest wavelength. So of those wavelengths, which are visible? Do you recall the visible range? The wavelengths that the human eye can see, the range of visible light, the only non-arbitrary part of the spectrum. Well, the range of visible light is from waves as small and high energy as 400 nanometers to waves as big as 700 nanometers with low energy.
All right,
Mr.
so yeah, going back to radioactivity. So we talked about how the nucleus of the atom was held together by the strong force, the one that's the best name in all of physics for the type of force, right, Mr. Mancino?
Absolutely.
Yes.
Worst named force ever.
All right, and without the right arrangement of neutrons and protons, the geometry, kind of like the shape of the nucleus, can't support itself. So when some atoms become too heavy, they have too many neutrons in comparison to their protons, the nucleus can't support itself. And what it does to make things better is just to break pieces of that nucleus off. And when that happens, a lot of times the element actually changes its identity. So let's look at a quick example.
Tie that into some of these P1 concepts with us.
All right, so let's check out this question really quick. So radioactivity and momentum is the title of this one. And it says a single unstable heavy atom initially has a negligible velocity. The atom undergoes alpha decay, resulting in the ejection of a high-speed alpha particle. And I remember an alpha particle is basically just a helium atom, and it forms a new atom. So which of the following correctly describes the total mass of the system before and after the decay? So I do remember us talking about something that said when two atoms are fused together, the total mass is now less than the individual components of that system. So what's going to happen in this case? If I undergo an alpha decay and I lose some mass, I lose an alpha particle, what's going to happen to the total mass of the system? So when I get rid of an alpha particle, a lot of times some energy is released, and that's because of the breaking the bonds of the strong force, right? So in this case, the total mass of the system is not going to increase. It doesn't stay the same. It actually decreases. And that's again due to that energy release.
Okay, so I don't get it, but I can accept it. That when an atom breaks apart, the total mass no longer adds up. But what about the conservation of momentum? That's a physical law. So same situation, the unstable atom breaks up. What describes the speed of the new atom? Initially, that unstable heavy atom is just hanging out with negligible velocity. A small alpha particle is ejected quickly. What happens to the atom, the new material that's left over? You may have called them superelastic collisions or explosions, but conservation of energy still has to work. The laws of physics hold. The new atom is moving, but it's moving slower than the alpha particle because the new atom is, well, heavy. It's heavier than the alpha particle. The alpha particle leaves with its momentum, and the new atom bounces away with its momentum.
So if the new atom is moving, but it's moving slower than the alpha particle, what do you think we can say about the momentum of the system before and after the decay? So I think we went over something that needs to be conserved: energy, momentum, and this one's specifically asking about momentum. So I think the momentum of the entire system is going to stay the same.
And indeed it does. But you brought up energy. What about the kinetic energy of the system? I mean, I know that in some cases, total energy is conserved. So what's going on here? The atom is initially at rest. It ejects the alpha particle and the daughter nucleus goes the other way. But what about the total kinetic energy of the system? Well, the atom starts at rest. If the atom starts at rest, it starts with zero kinetic energy. It used to have zero kinetic energy and now stuff's moving. So it doesn't have zero kinetic energy. The total kinetic energy increases. That means that the atom lost energy, and it lost energy in the form of mass.
All right, so half-life. If you remember, we talked about half-life being the time for half of that sample to decay if it's a radioactive sample. And just a quick example that we did last class is radium-226 has a half-life of 1,620 years. After 1,620 years, a 100-pound sample contains half of what it originally contained. So now it's still just 50 pounds of radium and 50 pounds of byproducts from that decay reaction. So what happens after 3,240 years? The 100-pound sample goes to 50 at 1,620, and another 1,620 years later, half of that half still exists as radium, which is 25 pounds. What happens to the other 75 pounds? It just turned into radium byproducts.
So here's one with a shorter half-life, phosphorus-32. The half-life of phosphorus-32 is about 2 weeks, give or take. So if we have a bunch of phosphorus-32, we're watching it, what are the odds that any one particular atom of phosphorus-32 will decay in a period of 4 weeks? 0%? 100%? Somewhere in the middle? Well, radioactivity is a statistical process. It's governed by the laws of probability. In any half-life, any 2-week period for phosphorus, in that half-life, there's a 50% chance that an atom, a particular atom, will decay. And after 2 half-lives, there's another 50% chance. So 50 plus 50% of 50 is a 75% chance that a particular atom will decay. So there are 3 types of radioactive particles that we talked about. We talked about alpha particles, we talked about beta particles, and we talked about gamma particles. And I know that you remember a bunch of those details. So alpha particles, beta particles, and gamma particles. There we are. Alpha particles are just helium nuclei. There we go. They have a nucleon number of 4, that's 2 protons and 2 neutrons, but a charge of only 2. Alpha particles are really, they're easy-ish to steer with a magnetic field. You can kind of steer them with a magnetic field. You can accelerate them with an electric field, but they're a lot heavier than beta particles because beta particles are electrons. Beta particles have negative charge. Beta particles are emitted when a neutron, a neutral neutron, becomes a proton and ejects a beta particle. That's right, there's a kind of nuclear decay that increases the number of protons without changing the number of nucleons. It converts one of the nucleons, the neutron, into a proton. And finally, there are gamma rays. Gamma rays are very short, high-frequency photons. They have no charge. They're light waves. They can't be deflected by a magnetic field. College Board also likes to talk about positrons. Those are particles with the same mass as an electron, but the opposite charge of an electron. So in the next question, we'll look at what's going on with some radioactive emissions as they enter a magnetic field. So there is in physics, we always combine ideas across topics. It's one of those important skills in physics, bridging your ideas across topics and domains. In this question, we're talking about radioactivity, but also the magnetic force on a particle. So your job is to figure out what particle 1 is and what particle 2 is based on the way that they turn in that magnetic field. Now, I'm guessing your teacher has worked with you on figuring out the right-hand rule for charged particles as they move through a magnetic field. Every teacher teaches it differently, so I won't show you mine. But if you apply your right-hand rule to those particles, you'll realize both of those particles have a positive charge. The velocity is toward the top of the screen. The magnetic field points into the screen, and however you apply the right-hand rule, you go ahead and do it. But what I also see is that particle 2 has a much wider radius. So whatever's going on, particle 2 is harder to steer. It's harder to turn. Well, for a particle with less mass, it's easier to turn. So particle 1 is a positron. Particle 2 is that alpha particle.
That was a good question. I like that one. All right, the next one. We're talking about a beta particle and a gamma ray are emitted during the radioactive decay of a nucleus of 214 lead-214. Which of the following is the resulting nucleus? All right. So with a beta particle, what happens when we have a beta decay? I think that we basically just get the ejection of an electron. But if we're ejecting an electron, what else has to change? I think in this case, we're going to change the atomic number from 82 to 83. So I'm gaining a proton. And when I do that, I'm actually changing the identity of the atom itself. But the mass number in this case is not going to change according to our rules that we've already discussed. So C is going to be the correct answer for this question. It changes into bismuth, right?
Okay. So in this course, we don't do a detailed treatment of the effects of objects moving at an incredibly high speed. It is a qualitative, non-quantitative treatment. If you get the opportunity to study this stuff at a university, though, really dig into it. It will impress you. It is amazing. Einstein left us with some important ideas. He reasoned that measurements of length and time depend on speed. That means that properties of space and time can't always be considered absolute. Everyone measures the same speed of light, but we don't measure anything else the same way if there's mutual motion between people. So for someone or something traveling very quickly, time is perceived differently than it is for someone moving at typical everyday speeds. For example, a muon is a fundamental particle. A muon at rest has a half-life of about 1.5 microseconds. So if you were watching a muon at rest and the muon were at rest, you would agree that the half-life is 1.5 microseconds, and the muon, if it could agree with anything, would say, yep, my half-life is 1.5 microseconds. But if a muon is moving at relativistic speeds, if we accelerate it in a lab to incredibly high speeds, we might measure a half-life of 1/4 of a second. Now that's a lot more than 1.5 microseconds. So why does that happen? Why does the half-life of a muon depend on its speed? Half-life, I thought, was just a property of a material. Well, it has nothing to do with the likelihood of decay being inversely proportional to speed, nothing to do with its size changing at high speeds. And it's not more likely to pass through other particles and avoid collisions that result in decay, because that's not what causes nuclear decay. No, in the muon's frame of reference, in its moving frame of reference, time is moving differently for the muon.
All right, so let's review photoelectric effect. So remember that photoelectric effect has to do with the surface of a metal, and when light is shined on it, when it's incident on it, it's able to emit an electron, or however many according to the equations that we talked about. So the interesting thing about this, though, is you may have remembered your chemistry teacher talking about the sea of electrons. And that means that the electrons on the surface of the metal are only bound by a small amount of energy. And again, when light shines on that, a lot of times the photons will enter the surface, the photons of the light enter the surface and collide with atoms of the metal and are totally absorbed. Now, a photon can give its energy to an electron, and if it's absorbed, if the energy absorbed is great enough, larger than the work function, the electron can break free from the atom. The photoelectric effect is also a result of collisions between photons and electrons that knock the electrons out of the metal. We can think about that two different ways, just in terms of energy or in terms of collisions. And just to refresh yourself a little bit on the equations from yesterday that we used, E equals HF, E equals HC over lambda. Do you remember how we converted that? And we also know a little shortcut that helps us is that HC is equal to 1,240 electron volt nanometers. That's the number that we're going to be using in our practice problems.
And speaking of practice problems, here's one of my favorites about the photoelectric effect. Now, I'm guessing that when you studied electrostatics, you looked at a device called an electroscope. An electroscope is that device that you see on the left. Your teacher or you probably applied electric charge to that ball on top, and you saw those metallic foil leaves spread apart from each other when they became charged. That's how an electroscope works. So ultraviolet light shines on that sphere. You see the purple light on your screen, and the leaves move apart. Well, why do they move apart? Deep thoughts. They move apart because the ultraviolet light is making charge move. The light is interacting with that metallic sphere, and the leaves are becoming charged. But when we shine green light on the sphere, the leaves don't move. Why don't they move? Well, you may recall from yesterday's discussion of the photoelectric effect that light needs to have some certain minimum amount of energy. It was in the review problems, that critical frequency. If light doesn't have that energy, it doesn't jostle, it doesn't move the electrons. It doesn't cause charge to flow. And I'll spare you the extra words. Notice in the picture, the light gets brighter, even if the light gets brighter, so that the green light is bringing the same amount of energy as the purple light. It still doesn't dislodge electrons because no individual green photon has the energy to move around an electron in the sphere.
All right, you may recall from yesterday, we talked about the maximum kinetic energy of that ejected electron is going to be equal to the energy of the photon minus the work function. And again, we can kind of substitute HC over lambda in there because that's typically what you're given in a problem from the AP exam. And notice that this is just a conservation of energy statement. That's all it is. So HF is the total initial energy of the photon. And if you look at the next to last line, it says kinetic energy of the electron plus the work to break it out has to equal the total final energy. This is why we're saying that this is just a restatement of the conservation of energy. Energy before plus the work done has to equal the energy after.
You know, that brings me right back to physics 1. But there were a few things that classical physics couldn't explain. See, intensity, it measures brightness, how many electrons there are per second, how much energy they're bringing. Brighter light should be able to dislodge electrons. Even if dim light doesn't have the energy, bright light should have the energy to do it, but that doesn't work. It's all about the frequency of the incoming light. The energy transferred to the electrons depends on the frequency of the light, not the brightness. Certainly, current depends on brightness. The number of electrons emitted per second is related to the number of photons hitting the metal every second. So even if the light is really bright, if it has too low a frequency, nothing is going to happen. The kinetic energy of the electrons is independent of the frequency of the light. Brighter light doesn't make more energetic electrons. It makes more electrons, but it doesn't give them any more energy. And the only good explanation for that is that light is acting like a particle in the photoelectric effect. That light is acting like photons. Each individual incident photon causes the metal to release a single electron, and more photons per second release more electrons per second. Well, Mr. Eaton, if we can treat light as a particle, then it must have momentum, right?
It does. So momentum of a particle we know is just mass times velocity. And the momentum of a photon is Planck's constant divided by its wavelength. But what's interesting about this is if we can treat particles and say that they have a wavelength, we can say the wavelength of a particle is Planck's constant divided by its momentum. So a particle being you, if you're running, if you're in motion, you have a wavelength. And the wavelength of a photon, that one's pretty easy. We talked about that several times. That's lambda is equal to c over f. So we can treat particles having momentum and photons having momentum and particles having a wavelength and photons having a wavelength. It's all almost interchangeable.
Does any moving massive object have a calculable wavelength?
I think so. I really think so. Even this guy.
Who's a good boy? So the reason you don't notice your own wavelength is, why don't we notice that macroscopic objects don't have a wavelength? All forms of matter have calculable wavelength, Planck's constant divided by their momentum, but I know that I don't diffract. I would notice that. So what is it? Why is it that you don't notice your own diffraction? Well, Planck's constant is a pretty small number, and your momentum is a pretty big number. Even if you're not moving real fast, you're in motion. You have appreciable mass. So a small number divided by a pretty big number is a pretty small number. Remember that to experience diffraction, the wavelength of the thing being diffracted should be, give or take, times 10 or divided by 10, a factor of 10 related to the size of the aperture through which it travels. So for that dog, if its wavelength is Planck's constant over its momentum, and that's Planck's constant divided by mv, it's about a 10 kilogram dog with a speed of about 5 meters a second. It's zippy, but it's not real fast. It's only a puppy. That's a wavelength of very small, 1.32 times 10 to the negative 35 meters. That's a very small wavelength. I don't have any doors that are 10 to the negative 35 meters across.
All right, one final note about diffraction of electrons. This is where we ended yesterday. The Davis and Germer experiment just shot a stream of electrons through nickel, and it measured a pattern of maxima and minima on the other side of the diffraction grating. And that just means that electrons exhibit diffractions. And if you remember the word diffraction, what does that identify? That the electron is acting like a particle, or is it acting like a wave? Do you remember the picture of the ducks in the pond where waves add up, waves subtract? They have maxima and minima on the other side of the screen. So that means that this experiment identified that electrons behave as waves as well.
So we did it. That's everything that you needed to know about modern physics to be successful on a high school test, if fingers crossed you're going back, or if you're taking this course for credit at a university, now you know.
All right, so here are our guided practice questions. We're going to answer 3 questions today. The first question is about Compton scattering. The second question is about electron diffraction. And the third is also about electron diffraction. So let's take a look at our first question. It says a photon scatters from an electron that is initially at rest, as shown above. Which of the following is true of the wavelength and the frequency of the scattered photon compared to those of the incident photon? So notice the incident photon is coming in from the left-hand side of your diagram, strikes the electron moves up and to the right, and the photon scatters down and to the right. So what's going to happen? If that photon strikes an electron, is it going to lose some energy? Yes. If it loses energy, which one of those 2 categories that you see, wavelength or frequency, if it's losing energy, which of those 2 is going to be smaller? And I say the frequency is going to be smaller, so that immediately gets rid of answer choice B and D and E. That leaves me with A and C as my choices. So what's going to happen to the wavelength? If frequency goes down, what has to happen to wavelength? I know that there's an inverse relationship between those 2. So if frequency goes down, the wavelength must get larger. So answer choice A is the correct answer for this question.
All right, but remember, electrons can diffract. Just like in the last slide, photons can collide with momentum, electrons can diffract. So here we see an electron diffracting through a crystal lattice. And the signal on the other side is recorded on a screen. Now, a student says this is evidence that electrons exhibit wave properties. Sounds like a smart student. I bet that's what you're saying too. Which of the following statements justifies the claim that this is evidence of electrons having wave properties? Read through those options. Okay. The best part of this question is that all of those are true statements. A, B, C, and D are true, but only C tells me why this justifies that claim. The pattern of bright and dark spots is exactly what I would expect from wave diffraction. That means that electrons exhibit wave-like properties.
All right, and your last guided practice for today. It's talking about electrons being accelerated through a potential difference, and they're incident on a crystal. The resulting diffraction pattern is observed on the screen. If the potential difference is decreased, the spacing between the maxima of the diffraction pattern increases. So the spacing of the dots on the screen are getting further apart. Does this increase in spacing support the wave model of matter? And why or why not? So what is changing here? The potential difference is changing. It's decreased. So I know that if I decrease the potential difference, that gives me less energy. And if I have less energy, what part of the wave is smaller? So I'll give you a second to look through those answer choices. All right, so if I decrease V, that decreases the speed. and it decreases their momentum. The electron's de Broglie wavelength is lambda is Planck's constant over momentum. So if lambda increases, lambda is going to increase here because the momentum is smaller. So if I strictly look at lambda equals h over momentum, since momentum is smaller, lambda has to be bigger. So answer choice B is the correct answer for this one.
We did it, everybody. Congratulations. Here are the key takeaways we're hoping that you are walking away with today. Did you learn about fundamental particles, that electrons orbit the nucleus at discrete energy levels? I hope so. How about that the strong force holds the nucleus together and is the best named force? How about the types of radioactive decay? Could you maybe discuss properties of alpha, beta, gamma particles? Could you talk about half-life? How about the idea of relative motion at relativistic speeds? The idea that measurements of space and time are not always consistent between observers in different reference frames. Could you come up with evidence that light behaves like a particle and that it behaves like a wave? I hope so.
And can you answer this question? If you were in a spaceship and you're at the front of the spaceship at the window and you're traveling at a significant fraction of the speed of light forwards, and you shine that laser light forwards, how fast is that laser light? How fast is a single photon of that laser light traveling forwards? Think about that.
So we're done. We did it. We got through all of the new material that you had yet to learn for the course. So your homework, what you need to do for us this weekend, tell your friends, tell your classmates that this is the schedule. Here is when we are doing review on all the different topics, starting on Monday and ending on May 1st. So take a screenshot of this. We're talking about fluids for 4 days, thermodynamics for 4 days, electrostatics for 4 days, circuits for 4 days, and magnetism for 4 days. Make sure that you watch the live stream for the material that you need the most. Customize this review for you. Let your teachers know, let your classmates know that College Board has this resource available and that they can use it for review. Finally, thanks for watching. We hope that you'll join us again as we begin to review the material that should be familiar to you from your AP Physics course.
And I think the review is going to be as fun as we've been having already. So have a great weekend, and we'll see you on Monday, hopefully.
Thanks, everybody.
This is the part where
laser at the front of a spaceship. Let's go.
I know, right?
No, it sounds like a really
it's a little bit of a tricky question.
Trip. I would do that.
Yeah. So we're supposed to make faces at Garrett now, correct?